rain cartoon. Usually you will get a page look like this. You will see a cloud with a lot of raindrops. Despite complaining about the raindrop shape is not what it should be in the real world, there are two other misconceptions. First, rain comes together with raining cloud in space and time in these cartoons, which is not necessarily true. And raining clouds becomes rain once the cloud particles falls, which is not true either. The rain comes after the cloud formation in both time and space. And this is probably what's really happened in the real world for a convective cloud. Oh, I don't know what's going on here, but don't worry about these details. This Holy Spirit type of convective cloud, you have this convective core and a big deck of anvil clouds and precipitation underneath. But within the convective cloud, you have the very small ice crystals that's oriented in different directions. They're not sphere. And you, when they grow bigger and bigger, you have larger ice crystals, and then they fall, forming snow, and they precipitate down. Once below the freezing level, they melt and become liquid droplets and eventually become rain onto the surface. So it experienced the whole microphysical processes before an ice crystal forming into the surface precipitation. So we need to understand the entire process using different measurement techniques in order to understand the entire cloud life cycle. And it's also important in terms of the energy budget because all the radiation occurs near the cloud top. What else do I put here? Yeah, that's it. So first, why it is important to have consistent ice-water path observation. In the GCM, you will usually have the ice-water path separated into the non-precipitating cloud ice-water path and the precipitating ice-water path. I combine here CIWP and PIWP, and they're the total ice-water path. And in the real world, in the measurement, satellite measurement, they don't separate it in this way. They just retrieve the ice-water path whichever this instrument is sensitive to. So there's not apple-to-apple comparison. So in order to make it more justified comparison, the Lee et al. Paper in 2014 tried to separate CloudSat measurements into the non-precipitating cloud CIWP and the total IWP and compare it to the model outputs. And you can see these are all the CMIP 5 model outputs. And this is the CIWP, this is the total IWP. And you can see it varies a lot among all the models by 1 or 2 manifolds across the CMIP 5 model. So observational constraints is very much needed in order to make the model better. And in the real world, the visible and infrared technique is mostly sensitive to this non-precipitating part, while microwave is sensitive to the precipitating part. So we want to have smart ways to combine their strengths together in order to get the total. But if we only compare the mean, what would it look like? This is the latitudinal distribution of ice-water paths in the models and in the observations, CMIP 5 models. So you can see in models it varies huge, especially in the mid-latitude and high latitude. But in observation, does it look better? No, it's not look better. The observational spread is also huge here among even, say, for Patmos, it's visible and infrared, but still it gives you a very largely biased observation compared to the CloudSat. The gray area includes the CloudSat observation, which we treat as a standard here. So that's why we need a consistent observation in terms of comparison to the model. We cannot just simply lump sum all the cloud and precipitating ice together for any comparison against the models. So in the first part, I will talk about the diurnal cycle of floating snow, why we care about floating snow. So the first thing is, of course, radiation. So if you decompose the global radiation budget of, say, outgoing long-wave radiation or the top of atmosphere albedo in the principal component analysis, the first component you will get is, of course, the sun. You will have the largest peak in the noon and the smallest in the midnight. But the second component is from cloud. And for the OLR, the outgoing long-wave radiation, the second component is directly corresponding to where the deep convective cloud occurs and evolves. And for the TOA, albedo, it's also corresponding to the marine stratocumulus life cycle as well as the convection cloud life cycle. So it is important for us to understand the cloud Dyno cycle in order to understand the energy budget globally. And what does the cloud Dyno cycle look like? We know that in GCMs, the cloud Dyno cycle looks not good. But what about reanalysis? We usually think reanalysis are good. Well, this is a comparison done by Dobson and Taylor. They pick up these Amazon convection active region, and this blue line is the surface precipitation rate they get from TRIM. From TRIM data, you can see it peaks around afternoon, around 17 local time. While in the Mero 1, if you compare the blue line, it just follows the sun. So it's not correct at all. And in Mero 2, it improves a lot. You can see the Dyno cycle, the blue line now looks much better, corresponding to what we observe. But still, it peaks early, like in 14, in the early afternoon versus late afternoon. And the amplitude is much smaller. So we can see some mitigation from Mero 1 to Mero 2, but still, the cloud Dyno cycle is not quite correct. So now let's talk about why it's important to have the microwave. Because usually when you consider about the energy budget, you only consider about the cloud top. But where does this visible and infrared observed ice cloud come from? They actually come from the cloud that microwave is sensitive to. Microwave observed ice cloud is the origin of the visible and infrared sensed cloud. They are just the old cloud that hang out there. And also, if you only use the infrared and visible sensor to use their retrieved cloud property, for example, the ice particle size, then you would only see the top layer of cloud, the ice microphysics, which is not representative of the whole column. So if you use those properties, that's largely biased in terms of the microphysics. And lastly, very importantly, in the microwave observed ice cloud, they precipitate. So they play a very important role in the hydrological cycle. So now we put them together. This is a very busy figure. I want to spend time on it. This is surface precipitation Dyno cycle in the tropical ocean and tropical land derived from GPM radar. So you can see tropical land has larger surface precipitation Dyno cycle, ocean has weaker, and the land one peaks in the late afternoon, which agrees with what we saw previously in the TRIM data. And this is from the geostationary data combination over tropics. And this is tropical ocean, tropical land, and this is 11 micron brightness temperature, so infrared channel. And this is a two-dimensional PDF. This is local time, and this is brightness temperature. So the colder the brightness temperature is, the thicker cloud is. So you can consider this is very thick anvil, and this is very thin cirrus cloud. So if you just follow the peak of the PDF line and draw the line here, you can see over ocean, it starts from like 9 in the morning, and where the thick anvils starts to dissipate into the cirrus cloud. And it takes a very long time, like 12 hours for this happen. And over land, it takes less hour, but still 6 hours for the thick anvils to spread into the cirrus cloud, finally dissipate over along this cycle. So these are just the infrared cloud where you see over here, and surface precipitation where you see over here. There's a link, a great portion of things happening inside, in between, where you don't see from only look at the surface precipitation and the infrared cloud. So this is what GPM, this is GPM microwave imager, which is the microwave sensor see. And this is the 166 gigahertz. I will talk about that later. And this is the same concept of this figure, but now this is the microwave. So this is the deep convection. It's very cold. And this is where the anvil cloud, so where infrared sensor also sees. So let's follow the peak of the PDF here. Over tropical land, the convection starts to develop in the local early afternoon, and then it develops very quickly. Only takes less than 2 hours for the development. Over ocean, it takes longer time, but still 3 hours for its development. So for the microwave, you can see actually the development from the hot air bubble near the surface until it reaches the middle to upper troposphere, where the infrared sensor starts to pick up the anvil cloud signals. And here you can see there's 2 regimes. The convection develops very quickly, and once it reaches the upper troposphere, it spreads out into anvils, and this takes longer time scale to develop. So this is the regime that overlaps with the infrared ice cloud. So if you go from the very from the deep convective hot air bubble and go upward, you can see the development of cloud life cycle is actually different in terms of time scale. And if you only use 3-hour temporal resolution, you would miss the entire development of the rapid convection. This is the TCR. I will tell about that later. So you can just think this is the cloud-induced radiance depression. So remove the clear sky signal, the colder it is, the thicker it is. So the pros of microwave sensor, it has day and night, so you can study the Dyno cycle. It has very long record. For the high-frequency microwave sensor, it has at least 30 years of record. So hopefully one day we can make the long-term record. And the high frequency, which means it's greater than 150 gigahertz, is actually dominated by the near linear brightness temperature and ice water path relationship. So it's pretty simple compared to other frequency regimes. But the cons is also apparent. It is not sensitive to thin ice clouds, so it will not be able to see all those infrared clouds. And there's unfortunately no geostationary platform, because microwave sensor needs a big antenna, and it's hard to carry out to the geostationary platform. So we have to deal with that. It's very hard to get a diurnal cycle from microwave sensor compared to like geostationary satellite, the infrared or visible sensor. And the brightness temperature ice water path relationship is subjected to very complex ice microphysics properties, and that's why we don't want to use a radiative transfer model to actually simulate this, because we already found that it has a great variability depending on the ice microphysical assumptions you use. So we want to use the empirical model instead. So this is the way we use. I think most of you are pretty familiar with the CloudSat. It's on the H-range, so it's fixed the local time, 1:30 a.m. and 1:30 p.m. But the good thing is that CloudSat scans through the cloud, so it can see from cirrus cloud down to the precipitation. If it's not too heavy precipitation, CloudSat is okay. And the GPM has 2 instruments. One is the microwave imager, which scans conically, and the DPR is the dual frequency radar working on KU-Ka band. It scans cross-track, so you can actually match the radar and the passive microwave together to get more information of the ice microphysics. And GPM satellite runs on this blue track, this precession orbit, similar to TRIM, but has larger inclination angle, so it can cover higher latitudes. But for our purpose, we only study the tropics. But the good thing is that the precession orbit gives us the different local time, so we can study the Dyno cycle. And GPM has all the high-frequency microwave channels that we are going to use. So it's suitable for this project. Let's first start from the very beginning, the PDF, the probability density function of the TB, what it looks like. So this is ocean, this is land, different TB for other high-frequency microwave. And this is from NPP, ATMS. This is from GPM, similar channels. So the first thing we can see is that we have a clear sky variability, which is the warm part, but it drops quickly because we're in the tropics. The land situation is more difficult, but over ocean, since the lapse rate is pretty stable, we have a small clear sky variability. And we have a very long tail in the cold part. So if we draw a line at the peak and calculate the spread of the clear sky variability and push it back here, you can say that this part is all clouds or microwave clouds, not necessarily infrared or other clouds. This is all the microwave cloudy sky things. And we will pick up all these things and do the ice water path retrieval. And the second thing we can see is that for ATMS, you have a lot of channels around the water vapor, 183 gigahertz water vapor line. So their spread actually can give you the differentiation of thick cloudy sky information that might be useful for the cloud profiling. That's one thing we're working on right now. And the last thing you can say is that the footprint difference. ATMS, the footprint is about 15 to 18 kilometers in terms of the radius. And the GPM has 4.4 times 7.2, which is much smaller. So you can see GPM can observe much colder things like 100K, while MPP ATMS doesn't pick it up. It only sees 120K. That's the minimum. So that means using a smaller footprint size passive microwave sensor, you can actually see larger ice water paths. In other words, thicker clouds. So now this is our approach. First, we define this variable called TCIR, which is called the ice cloud-induced brightness temperature depression. This is the difference between the measured brightness temperature and the clear sky-induced brightness temperature. For the clear sky-induced brightness temperature, we use the MERA-2 atmosphere profile as the input and use community radiative transfer model, CRTM, to compute the clear sky variability. So this is an example. You can see this is brightness temperature at 190 gigahertz, and this is the clear sky-induced radiance difference, and you can see the water vapor-induced depression can be removed from here. So after subtracting this one from this one, we can get the cloud-induced. So if you don't look at the white places, where it's 0, and black places, which is also 0, the blue places and blue and all the cyan and red places are where the microwave cloud lays. And that's where we're going to retrieve the ice water path. So this is the PDF look like after we subtracting the clear sky variance from the measurement radiance. And this is the TCR, what TCR PDF look like from ocean, tropical ocean and tropical land. And you can see the peak now is very close to 0. Although I still get some warm bias, I still try to deal with why there's a warm bias right now. I just do the bias correction to move all the peak to 0. And you can see the long tail from microwave cloud here. And they're separated, meaning that different channels are sensitive to different cloud thickness. So then we just co-locate all the GMI TCAR with CloudSat retrieved ice water path. The concept here is that we don't need to necessarily get the correct answer, but we want to get consistent answer. In terms of consistency, we treat CloudSat as the baseline. That's where we get our ice water path retrieval. This is all 4 GPM channel or GMI channels we use. And for each ice water path beam, I just normalize it by the largest value here, so you can see it better. Otherwise, it's dominated by the clear sky things because clear sky occur most frequently. And you can see this line. This is mostly linear until it saturates at very large ice water paths where the passive microwave cannot penetrate anymore. But the thing is that compared to our previous study using the NOAA-18 microwave humidity sounder, which is a cross-track scan, and this is all the collocations from near nadir view with CloudSat, you can see it looks much cleaner compared to the GMI. That's mostly because this is near nadir matches with nadir. CloudSat is also nadir. But for GMI, since it has 54-degree slantwise view angle, it's always mismatched with CloudSat in terms of the collocation. So there's a large variability, or you can say it's the inside footprint inhomogeneity that causes all these noisy points here. But however, if you look at where CloudSat says it's 3 kilogram per meter square ice water pass, for the near nadir view, you need like minus 75 Kelvin in order to get this much ice water pass. But for the slantwise view, you need only minus 50 Kelvin, which means the slantwise view can see larger ice water pass. That's a good thing. So this is a hurricane case from our previous study using the NOAA MHS. This is all the 3 channels, the high frequency microwave channels, what the TCAR look like, and this is our retrieved ice water pass. For the retrieval, we use the optimum estimation method since we have 4 channels, and we only need to retrieve 1 variable, so the error bar is pretty small. And this is the CloudSat overlay on it, and you can barely see any difference inside the hurricane. That means it's good. We matches very, very well with the CloudSat in terms of 1 single case. And this is NOAA MCPPS ice water pass retrieval using the same instrument, but you can see their ice water pass retrieval is much low biased. And this is the previous version of the MIRS retrieval system. So I don't know if MIRS is improved or not, but for the previous version, it's quite underestimated of the ice water pass. And this is what we got from the PDF in terms of climatology comparison. The black line is the CloudSat. So the PDF, the ice water pass PDF follows this log line for the CloudSat until CloudSat reaches its own saturation. And this is AIRS. AIRS is an atmospheric infrared radiometer. So it's working in the infrared regime, and it can see thin clouds, but then it drops. The PDF drops quickly as relatively thicker clouds. And the green line is from modest visible channel retrieval, modest operational retrieval, and you can see it picks up here, relatively thicker than the infrared cloud, but then it starts to drop once the cloud gets thicker. And this is biased signal here, which is means modest completely loses its sensitivity at large ice water pass. And the red line is our algorithm derived ice water pass climatology, and you can see it starts to pick up a thicker clouds, but then it follows CloudSat nicely until it also reaches the CloudSat sensitivity range. So you can see a nice overlap between different spectrum, and combining them together, that's where you can get what CloudSat sees. And for some other retrievals that's independent, for example, the ESCAPE, it's just way below the CloudSat. Look at this. Here is the log scale, so ESCAPE is smaller by 10. So we expect our GPM retrieval would be something like this. I haven't done that yet, but I expect it. And this is what currently GPM retrieval look like, the GPROF retrieval look like. This is from version 3, version 4, and version 5. This is just a scatter plot for CloudSat. This is GMI GPROF, and this is CloudSat ice water pass, or in the collocated points. You can see it just doesn't match up at all. But for version 3, if you look at the PDF, it agrees, not that bad, but for version 4 and version 5, completely off scale. So that means using the current GPROF algorithm, you are actually putting more ice into the raining part. They think it's raining because they use the DPR radar to train the passive microwave the observation. So they are they inclined to put more things into the raining part instead of the cloud part. So that's why they don't match when you go to higher and higher versions. Now let's get back to the business. Now we are using the same retrieval method, but now just applied it to all the GMI observation, and then bring it to different local time, and then we can get the diurnal cycle map. This is diurnal cycle map. It's pretty busy, but it's relatively easy to understand over tropics. This pointing up is the 0, which is midnight, and this is 6 o'clock in the early morning. This is noon if it's pointing down, and this is early evening, 18 local time if it's pointing to the left. And the magnitude of the arrow shows the magnitude of the diurnal cycle at different places. So the first thing you can see that diurnal cycle is, of course, larger over tropical land than over tropical ocean. And over tropical ocean, you can see larger diurnal cycle in the ITCZ region. So that's all pretty much agreeable with our intuitive understanding and other instrument report. And please just look at these two regions for comparison. These are the two land active convective region over Africa and over Amazonia region. And you can see most of the arrows pointing to 15. So it's early afternoon. And now let's put it into context with the infrared cloud and the surface rainfall. This is taken from by Jun's work in 2004, the infrared, geostationary infrared observation. And this is taken from, oh, I forgot to put the reference here. This is from TRIM PR, precipitation radar measurement of the surface precipitation. So let's focus on these two regions for comparison. And again, all the arrows has the same meaning as previous figure. But here, the author here used the color wheel. So you can see the greenish, yellowish color corresponds to local early evening, like 18 to 19 local time. So let's start from the infrared cloud. These two regions all have the infrared cloud peak near local noon, a little bit behind local noon. That's where the infrared cloud peaks in terms of the thickness. And then for the floating snow case where GMI are retrieved, you can see it peaks around 15 local time. And then for the TRIM, you can see over these two regions, it peaks in the evening time. So this basically shows you that the cloud, the anvil cloud, starts to precipitating and then eventually precipitating on the ground. It takes this whole life cycle from infrared to the surface precipitation in order to form this precipitation life cycle. And it's different from what we see from the brightness temperature PDF previously I showed, because that one shows you where the convection starts to form into clouds. And here, if you just do the average in each grid box of the thickness, what you get is actually the precipitation process. So the anvil cloud is forming into stratiform precipitation. So this is what the mean represents in here. So from the cloud to the snow to the surface rainfall. And if I just draw the mean in the whole tropical ocean mean and the tropical land mean, this is our retrieved floating snow ice water path over ocean and over land. And you can compare that. This is already misconceptive because you are lump sum a different cloud life cycle in different regions together. So, but still, you can compare it to the reanalysis output. This is Mero 2 ice water path. I just arbitrarily separate into clouds above 300 hectopascal, which is the black line, and the clouds below 300 hectopascal, which is the red line. So I think the below. Oh, sorry, I put these two wrong. So the floating snow is this one, and the cloud ice is this one. Is the black line. So you can see the diurnal cycle. This is all normalized to 1. So you can see the diurnal cycle doesn't match with what we observe in the real world. So that means we still have a lot of room to improve in order to get the correct precipitation cycle. So reach the conclusion for my first part. So this work uses a synergetic approach to extend the fixed local time CloudSat radar observation of ice water paths to different local times in the tropics. And this approach takes advantages of CloudSat's superb capability of profiling floating frozen particles and the advantage of passive microwave imager good temporal and spatial coverage. And this approach can be extended further to other instruments. We already applied to the MHS NOAA series, and we applied to here to the GMI, and we can apply it to other microwave sensors. For example, the Sapphire launched by French and Indian community, and the other instruments in order to get the ice water paths from different local time, different region of this world, or futures. And this once CloudSat is done, we can have future radar in the Earth Care or next decadal survey missions that can help us continue this record. And because high-frequency microwave sensor is only sensitive to large ice particles, it is only sensitive to thick ice cloud and floating snow layer. And this diurnal cycle is missing so far, and our study is the first one to show the diurnal cycle of floating snow. And precession orbit requires a lengthy period of observation. What I got for the GMI and CloudSat collocation takes 2 years of data, and we only get like 7,000 something in the tropics, which is collocation in terms of GMI footprint, which is very few. And that's one of the reasons why my PDF, collocation PDF figure looks noisy than the MH figure. So the precession orbit, we need to take a long time to construct this diurnal cycle and to construct the collocation sample. We can combine multiple microwave sensors to mitigate this problem, but we need to take care of a lot of other complicated problems like the inter-instrument calibration problem. The viewing geometry is different from sensor to sensor, and the footprint is different. As I showed before, the ATMS and GMI has different statistics, and that's partly due to the footprint difference. And using area or latitudinal mean as the metrics for the comparison is rather misleading. A PDF might be a better parameter to use in terms of comparison among different observations and between observation and model. And nowadays, the diurnal cycle of surface precipitation is still a big headache for even the most sophisticated GCMs. Like the MMF still has this precipitation diurnal cycle problem. And to solve this misplaced diurnal cycle of precipitation, we need to look up into where it comes from. That means the ice cloud and floating snow and a mixed phase cloud. And we need to always treat the entire cloud convection precipitation cycle as a whole. This concept is also called in the 2017 NASA Decadal Survey. So we're right now trying to work more toward this direction, how to make the measurement more coherent. And the next part is the diurnal cycle of ice microphysics we derive from the still from GMI. So we go back to this image. Now, if you look into more details, the ice particles are oriented differently. They could be randomly oriented, or they could be oriented in a preferred direction. That's what I show here. And how passive microwave can give us this information. And also, this microphysics, does it have a diurnal cycle? Because in our previous retrieval I presented in part 1, it all assumes that the brightness temperature and ice water path relationship remains the same for different local times. That means the cloud ice microphysics should remain the same throughout the cloud diurnal cycle. And is that the case? So that's the second part, what we want to study. In the real world, we know ice particles have different shapes, and it's depending mostly on temperature and supersaturation. But in the model and retrieval world, we treat it rather simple. Even right now in the model collection 6, it has one shape assumption for all the ice particles and for the retrieval. So the ice crystal microphysics properties we talk here, including the shape, the size, the density, and the orientation. And what we're going to focus is the orientation. So this is one story from the passive visible sensor from Discover, the EPIC instrument. So this is an image you took from EPIC. And then if you look closer, you can see a shiny spot here, which means the ice crystals here are preferentially horizontally aligned. And for the visible light, they act like effectively as a mirror to reflect the sunlight back. And that's why you get a spotlight here. That's what you get from visible. And this is also seen from other active sensors like Calypso and passive sensors like Holder. They all see horizontally aligned ice crystals. But remember, what they see is very small ice crystals because Calypso and Holder and Epic, they all work in the visible light range. And if polarization difference is identified in the microwave spectrum, does it see the same property we see from the LiDAR or passive visible light sees? And what about, we can even ask, what about near infrared and far infrared? And these are some literatures that's discussed before of the microwave polarization difference. And this is how we define the polarization difference. Because for the GMI, we have polarized paired channel observations at 166 gigahertz, which means it has measurement at the vertical polarized channel and horizontally polarized channel at the same frequency. And we define this PD called polarimetric difference, which is difference between these two. So imagine if you have an ice crystal that's not sphere and it's horizontally aligned, for example, if it's a plate, then the vertical polarized wave and horizontally polarized wave are going to penetrate different, experience different different optical depths. So their difference would tell you where it's oriented. And if it's horizontally oriented, this polarization difference is going to be positive. And if it's vertically oriented, the polarization difference, PD, is going to be negative. So what GMI sees? Let's go to this figure first. This is a case study, a squall line case. This is 89 gigahertz, 166 gigahertz. Let's first focus here. For the brightness temperature, you can see the deep convection develop along the squall line and the big anvil surrounding it, which is relatively cold, mediumly cold, and the clear sky is very warm in the 166 gigahertz. But for the polarization difference, you can see it's very small along the convective line, very large in the anvil cloud, and again, go back to very small in the near ambient clear sky region. So if you plot it out as a scatter plot in terms of brightness temperature versus the PD, you can see it bears with this upside-down bear curve. For 89 gigahertz and for 166 gigahertz, they are the same. And the peak is always about 10 to 12K, 10 to 12K here. Albeit for the 89 gigahertz, you will see a lot of ocean surface wind signal here. That's corresponding to this region where you don't have wind, so ocean surface is quite polarized. But for 166 gigahertz, you don't see it here because in the tropics it's quite humid. So 166 gigahertz is the surface signal is blocked here, so you don't see much signal here. And this is a simulation done by Joe Monchak. He simulated which channel, basically the weighting function for each channel. So this is the weighting function to the ice-water path for 89 gigahertz and 166 gigahertz. And you can see that 89 gigahertz is mostly sensitive to the ice-water path close to the surface, 2 to 4 kilometer. And for the 166 gigahertz, it's mostly sensitive to the ice-water path in the middle troposphere, 4 to 10 kilometer. That's where the 166 gigahertz ice-water path is sensitive to. But when you vary the ice particle orientation, you can get the largest sensitivity at 166 gigahertz, also in the middle troposphere, where the 166 gigahertz vertical polarized minus horizontally polarized gives you the largest weighting function. This is not exactly a weighting function. This is just a response, showing you which variable is mostly sensitive to which parameter. So the PD is mostly sensitive to the orientation of the ice particles. That gives us the theoretical backup of what we see here. And what about submillimeter range? This is one field campaign result we get from ER2 COSIR instrument, where it works on the 640 gigahertz, the sub-millimeter range, and you can see pretty much the same thing. This is just one case. So it's quite noisy, but you can see the same thing. It also peaks around 10 Kelvin, and it also bells with this bell curve. So this bell curve, with the upside down bell curve, we say it's like a universal thing for the microwave and sub-millimeter range, as long as you are looking at the PD and the brightness temperature relationship. So now let's look at the bell curve. This is the bell curve, the PDF, and if you link the peak of the PDF, you can get this bell curve. And this is what the bell curve looks like over tropical ocean and over tropical land in different local times. So you see over tropical ocean, very little difference. Over tropical land, large difference here. This is the region we're going to focus on. And this is also from GMI. We also bin it into different local times, separated by 2 hours here. But you can see over land, it has as much as 35% difference, and over tropical ocean, you can only see as much as 6% difference. That means the ice microphysics is actually changing as much as 35% during the cloud life cycle. So if we plot the peak here as a function of local time, and this black line is what we get for tropical land and tropical ocean. So you can see over tropical ocean, the ice microphysics doesn't change very much. But over tropical land, you can see it peak in the local morning, and that reaches the minimum in the local early afternoon. And if you overlay the red line is the precipitation derived from DPR radar, and the blue line is the cloud mean brightness temperature, which corresponds to the ice water path, the cloud thickness. And you can see they are anti-correlated. And further on, if I do the lag correlation between this black line and the blue line, and the black line and the red line, you can see that both over ocean and over land, their anti-correlation does not occur at 0. They occur at 2 hours here. That's the lag correlation, means the ice microphysics change is actually leading the ice macrophysics change by 2 hours. That's what we are arguing here, that ice crystal microphysics have strong diurnal variation over tropical land, and the diurnal cycle of ice microphysics is tightly related with ice cloud and surface precipitation evolution. And then let's take a look at the sensitivity to the temporal resolution. If we use 2 hours as the temporal resolution, the lag correlation happens at 2 hours here. If we use 1 hour, it also happens at 2 hours. But if we use 3 hours, of course, it's shifted to the 3 hours. So the lag correlation is actually distorted if we use 3 hour temporal resolution. So that's why we're thinking that you need to have higher temporal resolution in order to understand the microphysics evolution with the cloud and precipitation life cycle. So the conclusion for this part: first, the high frequency passive microwave can retrieve the floating snow ice water path, and the polarimetric measurement is very powerful to reveal the ice microphysical properties, especially the orientation. We have done a lot of simulation studies, and I don't have time. I don't want to dig into all those subtle details, but the bell curve is sensitive to the particle size and the particle shape and the orientation. So it's a combination effect. Yeah, that's basically what I put here. And right now, Joe Monchak and Ian Adams in the Goddard GPM team, they're working hard on using the three-dimensional the Monte Carlo method to retrieve this, and we're progressing step by step to disentangle the shape, size, and orientation information in this polarization difference signal. And precession orbit helps us to understand the ice microphysics diurnal cycle, and we know that ice microphysics diurnal cycle has up to 35% change over tropical land, and this would result up to 50% error in the ice water path retrieval. So in our previous retrieval, if you don't consider the mass microphysics change, it's embedded with another error source. And the diurnal cycle of polarization difference leads that of the ice cloud and precipitation macrophysics property change, meaning that understanding the variation of ice microphysics is necessary to predict, infer, and model the bulk properties of ice cloud and precipitation and related processes. And for details, I have these 3 papers and other references if you're interested in. And I just want to go to one little detail, just give you a little bit flavor. So this is the bell curve we see. And for region 1, 2, 3, if you just consider the brightness temperature, they will give you the same ice water path, same thickness, correct? But if you draw the collocated CloudSat radar reflectivity and collocated Ka band radar reflectivity, you can see this 1, 2, 3 region actually showing different types of cloud. The region 1 with the largest polarization difference actually showing you the largest CloudSat reflectivity in the middle troposphere and the smallest reflectivity in the upper troposphere. So they are actually corresponding to different cloud regimes. So you cannot just simply retrieve ice water paths from using the brightness temperature only. They actually have different microphysics behind it. That's the last flavor I want to give it to you. But this is very preliminary study. So we're arguing that it's corresponding to the precipitation process afterwards, because you can see the melting band is different for different cloud regimes here. So I want to end up here and taking any questions here.
Questions?
Hopefully I'm not overwhelming you.
I try to understand the polarization difference.
Yes.
Showing there over ocean, over land.
This figure?
Yeah, yes. This showing here is over ocean is pretty stable.
Right.
This is just for the ice cloud.
Just for whatever the you mean the blue line or the red line or the
blue line?
The blue line.
Yeah.
Yeah, the blue line is just for the ice cloud. So the blue line is sorry, I didn't. The blue line is actually the average of this thing. I also did the average over here. So basically all the ice cloud that's 166 gigahertz reporting. So the blue line corresponds to the ice clouds. Yes.
All the time, the average over the time, or is some specific time?
This is the local time. So
okay.
Yeah, average over local time.
So that means for the whole day, the macrophysics of ice particle is not change over the ocean.
Not change much over ocean, right?
Okay.
But over ocean, your entire cloud cycle, diurnal cycle, is also weak. So it's quite consistent with the whole picture. The cloud diurnal cycle is weak over ocean, no matter microphysics or macrophysics.
Okay, so that also means for the ice cloud over ocean, the microwave radiation is pretty stable.
Yes, over ocean, yes.
Over ocean.
Yes.
Not only the polarization difference, but
right.
the absolute brightness temperature also very stable over this.
In terms of the diurnal cycle. Yes.
Okay, thanks.
Yes.
That was a very nice talk, very comprehensive. You may have said this, but the diurnal variation you're talking about over land here with the PD, I think you might have said this. It's related, I think, or maybe you said it's related to the type of the diurnal variation of the convection. When you have intense convection, you're going to have more spherical particles, I think.
Right.
And that's what's causing, so your variation there. And after post deep convection, you're going to have a lot of oriented particles. Is it basically that simple?
Well, I don't think that's that simple. In our paper, I actually give several possible explanations. We're right now working on it. So one explanation is, let me see. This is the simulation we done before for this bell curve, and the separation is for different shape, for different size, and these four figures for different shape. So you can see it's largely the curvature of the curve is largely dependent on the shape and also the size. But here we all assume 100% orientation. But if you go back to the schematic figure I showed in the very beginning of this talk, where is it? Here. So what you are saying is that in the deep convection region, you might have a lot of tumbling, and you may bring large particles over to the top. That both of those mechanisms could decrease the polarization difference inside the convection, and we don't know if that's the case because all of our radiative transfer simulation don't have the dynamics play a role there. We only know that in the anvil, probably ice particles tend to be horizontally aligned because in anvil you don't have up and down vertical movement. So likely, if you have non-spherical particle, you tend to be horizontally aligned. But in convective core, what causes the diminish of polarization difference? We're still not sure if it's radiation, or it's turbulence, or it's both. It's quite complicated.
I thought it was fairly well established that deep convection you have more spherical particles, and that's related to that, but I'm not sure. That's also over ocean, where you don't have much of a variation in the polarization difference.
Right.
I mean, convection is generally weaker over ocean, so you don't have as much spherical type particles in the upper part of the cloud as you do over land.
Right.
You have.
But the one thing is that for the radiative transfer model simulation I just showed, those four tiny figures, I don't need any convection assumption like turbulence or different particles or more sphere-like particles in order to get the bell curve. To get the bell curve, I can assume 100% orientation everywhere. I still can get the bell curve. I can get it diminish at very cold brightness temperature. So we're still debating whether it's radiation or it's, different particles are sending here or tumbling.
While I have the microphone,
Yes.
another question. You compared to GPROF, and you showed there were some issues with the PDF of the ice water content. But if you look at the diurnal variation of ice water path in GPROF, does it give you anything like?
I don't know. Honestly, I didn't look at it.
You didn't do that?
No.
I mean, because it supposedly gives you a vertical profile, and I don't know at what, vertical resolution. But it would be interesting to compare with, even if it's getting the total amount of the ice water path wrong, is it getting the diurnal variation correct?
Yeah, that's a good suggestion. Yeah, I will do it. Thanks.
You compare this with the surface precipitation.
Yes.
So all your results, do you actually sample this or separate this for raining and non-raining clouds? Are they all raining clouds?
Yeah, that's
You don't separate them, right?
no.
You just
That's one thing I think my caveat, the caveat of my research, and the caveat I said in the conclusion of the first part. If I can put it over here, you cannot just simply use the mean of the whole tropical land to represent, right? Each grid box, each region, and each different cloud regime, like it's stratiform precipitating or it's developing case, it's all different.
Yeah.
So you need to separate it in different regimes.
Yeah, but your curve, you didn't separate into regions.
No, in my curve, I
you
didn't.
haven't done it yet, but you want to do it.
I want to do it, but the problem is for GPM, you don't have enough sample. Even I have 4 years of data already. In order to construct the diurnal cycle, if you further separate them into different regions, different regimes, the statistics is going to be bad. So we need more data coming in, honestly. Yeah.
Okay.
Yeah.
So it's a mixture of all types of clouds, rain.
Right. That's
uniform,
one caveat
convective,
of
and-
my research.
and
Yes.
Raining and non-raining too, right? Yeah, you mix them because you didn't distinguish.
Right. Raining and non-raining in which figure?
In general, I'm thinking of your properties that you derive, right? The bell curve, for example.
Yeah, let me see. I divided by the total overpasses of GMI. So yes,
Yeah, you don't
divided by
distinguish.
total.
Yeah,
Right.
yeah.
Yes.
It could be very convective cloud and still not raining, depending on the stage of development.
Right. You're right. Yeah, and how to separate that from a passive sensor, just one overpass? You cannot do that, right? So that's one of the complications. You have to have multiple, and they are well calibrated with each other in order to say whether it's developing or it's decaying, right? So it's hard.
Okay, so thanks to speaker again.
Thank you. Happy holidays.